Okay, so this is what we'll talk about on Wednesday, but actually we can cover a fair amount here because the problem's pretty simple. So this is about this problem called subset sum. And it's a problem that you've probably seen a lot. I'm gonna skip this intro since we just did it. A lot of intro. Okay. Well, actually, I don't know if you do it anymore in modern days, but let's say that you had 93 cents. So in the American currency system, which you may or may not have ever used, quarters are worth 25 cents, dimes are worth 10, nickels are worth 5, and pennies are worth 1. Okay? In the old days, when people use vending machines and stuff, right? So if you had 93 cents and you wanted to turn it into quarters, dimes, and nickels and pennies, what would it be? How many quarters? 3? How many dimes? How many nickels? And how many pennies? 3. Okay, so we've all done this maybe. And, right, this is pretty simple, right? Okay, so that's basically the problem. Uh, I'm going to give you as input n integers, okay? And I'm going to give you a target t. I forgot to write t. Okay, so that could be 93 cents. And my question is, can you find a subset of the input integers that add up to t? Okay, so I give you a bunch of numbers and a target number like a million. Can you find some of the target input numbers and add it up to a million? Okay. This could also be a yes/no question. Is there a subset that adds up to t? Okay. All right. So here's an example. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different numbers and a target of 52. Is there a subset of numbers that adds up to 52? If I once knew the answer, I no longer do. I made this a couple years ago. Anyone find a way to add up to 52? No? Ah. Yeah? How did you do it? Sorry? 14, 18, that's 32 plus what? 10 and 10, 52. Yeah, I think I did 14, 13, 17, 18. That's 34, 52. Okay, so at least two solutions. Okay. Uh, one thing, or you could switch 18. One thing nice is that if you do think the answer is yes, you can prove it, right? I can give you the numbers, and you can say, oh yeah, yeah, that does add up to 52. It's very easy to double check an answer. If the answer wasn't 52, I mean, if there was no way to add up to 52, it would be much harder for me to convince you there's no way to add up to 52. It's not obvious to me, at least, what would be a certificate, so to speak, a proof, something that I can easily check. So that's an interesting feature. But insofar as you can recognize a yes answer, we still call it a search problem. Okay. Okay. All right. We have at least time for a poll and more discussion, actually. Who thinks that we're going to get an algorithm for this? 1, 2, 3. Okay. I would say that's like, oh, I didn't ask who's not going to vote. Maybe that means more people will vote. I'll give you a chance now. Who's not going to vote? Okay. 3. And then who thinks it's going to be tough to get an algorithm? Okay. 2. Okay. Okay. So, all right. All right. Let's see what comes up next. Oh, algorithms. Okay. Any ideas for an algorithm? Many people thought we can get an algorithm for this. How would you go about it? Brute force. Okay, how would you go about a polynomial time algorithm? Oh, okay, can we do something recursive and then try to save our answers or something? Well, you're in luck. Okay, what would be a recursive spec? How can I break this down? So you're saying you're going to be given a subset of numbers, and t true if there's some subset that adds up to t, and false if not. Okay. Now in this formulation, so there's n numbers and so it's, n plus one numbers or something. How many subproblems are there? 2 to the power of n. So, so this is going to be a little bit tricky, right? In fact, not only that's 2 to the power n just from choosing subsets of xn. And if you're planning to change t, then who knows how many different ways you can change t as well. So as described, this isn't quite, how can we, if we want to do caching or if we want to do this dynamic programming, right? A recursive algorithm that saves its answers, we need to come up with a formulation that also limits the number of subproblems. We can at least try to address this part, the 2 to the n part. Yeah. At most k. Well, initially you're going to have n, so you're going to want to have all possible n in the beginning. Ah, they are ordered. So if I only look at like, oh, can you add up to this number using the first 5 numbers, the first 8 numbers, the first 10 numbers, that only generate, n subsets, right? And you can just pick off one at a time. So if we just add a little bit more order, it'll become more modest. Uh, okay, well, I wrote it this way anyway. Well, we'll come back to this point. Let's implement this uh, in the brief amount of time we have. So I think maybe this is what you guys had in mind. Well, okay, what's the base? What are some base cases? T is 0, the answer should be true. What's another base case? If there's no numbers left, but t is not 0, we should answer false. There's no way to add it up. And otherwise, maybe we would just try one of the numbers. I either take it or I don't, and I take it out of my set. Okay, so I think this was sort of almost on a homework, right? Yeah, so you can do something like this, right? Where I think this is what we just described. So this is saying, okay, I either don't use x1 and I keep the same remaining numbers and I try to add up to t, or I do use x1 and I subtract it. This should be a 2, no matter what it looks like. So t minus x1. Okay, so that's like from our week 1 homework practically. And how long would this algorithm take if it was this implementation? Exactly? A 2 to the power of n, because I'm just trying all these combinations. So, okay, but as mentioned, we could apply dynamic programming, right? So if I reword this a little bit and say, oh, it's numbers from I onward, right? Because that's what our algorithm was doing. It was just trying the first one, then the second, then the third. Then, I'm just advancing I. So I either don't use the ith number or I do use the ith number, same as before. It's just encoded a little bit differently, right? This should be if I is bigger than n or something. If I is bigger than n, that's when you have no numbers left. Okay. All right, so here's yeah, I have one more poll and then one more slide. So we're actually close to done. All right, given the algorithm we just did, uh, Who thinks we're going to get a polynomial time algorithm for this problem? Do the same people still feel like we're going to get an algorithm? Do some people change their mind and now think the problem might be hard? Okay, what inspired the change of mind? Oh, okay. Those who voted algorithm and changed, did anyone go from algorithm to hard? Oh, okay. Fine. Well, okay. So there's one catch. So NT seems like a great running time, right? Oh, you gave me T, and isn't that like really fast? Is that quadratic or something? But here's the catch. T takes only log T bits to write down. Okay. So T could have been like 2 to the n or something, even if all the n numbers were small, like 1, 2, 3, or no, if they were big or something, right? So T could have been huge, in which case NT is actually an exponential running time. Okay. So if all the numbers were like really tiny or something, you'd be okay, because maybe T would be small. But that's not necessarily the case. So in fact, we have not shown a polynomial time algorithm yet, but we're making some progress. Okay, so that is the suspenseful teaser ending the class, and we'll keep talking about this next time. So, right, we started this last time, so let me quickly recap and bring us up to speed where we left off. So, right, we've been talking about these really tough Boolean formula problems. Even 3-sat turns out to be tough. But then we had an interesting discussion last time where we looked at two variants. One was 2-sat, one was max 2-sat. And for each, you can ask the same question: is there an algorithm, right? And what did we find? We found that for 2-sat, you can get an algorithm. But for max 2-sat, apparently you can't. Okay, so we're able to show that 2-sat is actually just some kind of strongly connected component style algorithm, relatively elementary parts. And max 2-sat, which doesn't seem that different, turns out to be general enough to capture 3-sat and therefore capture any Boolean formula. Um, so this is quite surprising, right? There seems to be a very small distinction between 2-sat and max 2-sat, at least on the surface. And yet algorithmically, they're just worlds apart. One of them we can do as fast as you can imagine in linear time. The other we're no closer to solving than we are to solving Boolean formulas in general. Right, so there's something like very subtle going on here. And then we switch gears into what seemed like a relatively simple problem, which is roughly decomposing one number into the sum of many. So formally, I give you a set of numbers and a target number t, and I just say, oh, can you find a subset that adds up to t? Right. So it's sort of like making change out of coins, and most of us who voted thought that, okay, this seems simple enough. We should be able to get an algorithm. So we started working on an algorithm, right? And what we did was a recursive algorithm. Well, first you can just write out kind of the basic recursive algorithm. You either try taking a number or you don't. Of course, that takes exponential time. But if we do some caching and just rewrite it a little bit so it's sort of dynamic programming friendly, then we'll get an NT overall running time where T is a target number, N is a number of integers, and clearly the algorithm is not very complicated, right? All right, that might seem satisfactory, but if you look a little bit more closely, T actually is not really a polynomial running time, okay? because it only takes log of t bits to write it down. So when we talk about polynomial running times, we're really talking about polynomial in the size of the input, how long it took to write it down and give it to your computer. Okay. So t could be a billion, gajillion, gajillion, and in your algorithm will take n times a billion, gajillion, gajillion time, but it only took log of a billion, gajillion, gajillion, which is probably like 100 or something, to write it down. Okay. So this seems like a good algorithm, but it actually doesn't meet our requirements. This is where we left off. Uh, any other ideas? Our algorithm's pretty simple, so maybe we can do more. Yeah. Okay, maybe we can go a different direction then and try to show the problem is hard. Okay. Does anyone else have any algorithmic ideas before we abandon hope? Okay. Um, okay. So, all right. So, subset sum, the natural algorithm wasn't polynomial time. We couldn't think of any good ideas. So, all right, can we show that maybe it's as hard as satisfying a Boolean formula? And this feels like a bigger leap of imagination because at least to me, my opinion is that subset sum doesn't look anything like SAT. Like you might believe that 3SAT can solve Boolean formulas. You might believe that max 2SAT can solve 3SAT because those are at least formulas. Right? That doesn't really explain why we can do 2SAT, but at least most of the hard problems we've seen, have the same form. Here, we're looking at a problem that I don't know, if you're just making change for out of a dollar, it seems very, very easy. And in general, I don't know, it doesn't seem like adding doesn't seem like a very complex operation. Right? That's the only thing you can do is you can add things up. Nonetheless, what we are going to show is that a polynomial time algorithm for subset sum will get you a polynomial time algorithm for SAT. Okay, so this is a bigger leap than last time. Okay. What's down here? Okay. Um, well, any ideas? Here's one conceptual difference. So in SAT, let's say I give you 3SAT, right? That's nice and simple. So I give you a bunch of clauses with 3 variables each, and you have to satisfy all the clauses, right? And there could be many of them. That's what makes it hard. Subset sum feels different because you only want to satisfy one thing. You just want the numbers to add up to t, right? So one maybe challenge is to try to figure out like, okay, how can I use one target to try to encode many requirements, right? Somehow adding up to t in some kind of way. So I want to take a 3SAT formula and generate a subset sum, but there's one clear conceptual difference. How am I going to kind of simulate satisfying all these things at once with adding up to a single number? We start with a 3SAT formula, and now we're going to turn it into a subset sum. So I give you clauses, and you have to generate t, you have to generate numbers. So we're going to try to show that if subset sum can solve 3SAT, then subset sum is hard. Okay, we weren't missing something, some cute idea algorithmically. Yeah. Sure. So I think that, well, one could do either direction, but my guess is that if I asked you which problem seemed harder, you would probably say 3-SAT or Boolean formulas. Maybe you wouldn't. But I mean, we had a vote, right? Most people thought that we could have an algorithm for subset sum. So I personally feel like the statement that subset sum could solve SAT is a more ambitious statement than vice versa, which is that SAT can solve subset sum. Okay. So we could do both directions. The slides are set up for one. We're going to actually do the other direction later on in another lecture. But the initial question is, I'm primarily interested in just solving subset sum. This is a practical problem, right? You would think it was simple. We thought of an algorithm right away, although it wasn't quite polynomial time. Couldn't think of more ideas. Oh, I wonder why. If we could show that subset sum would imply an algorithm for SAT, that would sort of give us some kind of closure as to why we couldn't come up with a satisfying algorithm. So I guess the direct answer to that question is that we are interested in subset sum and either getting an algorithm for it or showing that maybe we won't get a satisfying algorithm. So it's just our kind of external motivation coming in. Okay, so but still, yeah. So let's see. What's okay? So let me map it out. Okay, so we'll start with some kind of 3-SAT instance. Let me put out the diagram, and then we will discuss it. And we want to somehow generate numbers. I guess these xi shouldn't be confused with these xi's. These will be numbers. Those are variables. And some target, and we should be able to give it to a black box. Okay, which will return either a true or false, and that should somehow map to a true or false for our formula. Okay. So if we can complete this, that'll show that this may be hard to come up with a good algorithm. And then to some extent we'll satisfactorily understand the problem. Okay, but still, this conceptual point, which is, it feels like in 3-SAT you're satisfying many clauses at once, and it feels like in subset sum you're just trying to kind of meet one requirement, which is making this number add up, right? So how could I even bridge that gap? Or how might I? It's not easy to guess, but maybe it's fun to speculate. Okay, could we have started with max 2-SAT, where the answer is a number, and then I'm not sure. I'm certainly not prepared for that as far as the slides go. Um, I'm not sure. I don't have a great answer to that. Yeah, I'll do max KSAT. Okay, so we still like this max idea. Okay, so okay, let's just explore this then. If I gave you a max whatever sat, 2, 3, 4, whatever you want, you're going to have to somehow translate that into numbers and targets. What might be the numbers or what might be the target? Okay, so T could be the number of clauses you want to satisfy. So we could turn into a yes no question. So max 2-SAT can either be like return a number, or I can say here's a 2-SAT formula and here's a number k. Can you satisfy at least k? And that's a yes no question, but they're basically the same. If you could do the yes no question, you can just kind of, oh, k is okay. Okay, what about k plus 1? What about k plus 2? And you figure out the right k, right? So they're actually equivalent. Um, Okay, so let's say, okay, so I give you some max 3 sat or whatever, and this target number k, you're going to turn k into t. That's the idea. Oh, k will be one of the x1. Okay. So remember, t doesn't exist. We have to invent t. No, you're given 2 sat. You're given 3 sat. Yeah, so we got to get the direction right. So we want to solve some problem we know that's already hard with subset sum. Yeah. Yeah. So if we show that subset sum could be used to solve 3 sat without actually giving an algorithm for subset sum. So we just say, oh, what if you had it? So we want to know how come we can't come up with an algorithm for subset sum? And what we're really asking is, what if we did? What would be the implications? And if it would imply an algorithm for 3 sat, then that would say, oh, this might just be a dream. So we don't have an algorithm, but what if we did? Is it realistic? And if you feel like it's hard to get an algorithm for 3 sat, but your imaginary algorithm for subset sum would give you an algorithm for 3 sat, then you might conclude, oh, we probably won't get an algorithm here. Yeah. Yeah, so that's what we kind of want to do. So if I give you a formula with m clauses and n variables, what are you thinking will be the numbers and what do you think will be t variable? Each Boolean variable is what? Becomes a number? Okay. Then what should t be? Hmm? Just a sum? No, we have to choose a t. We make a t, right? Well, maybe that's an idea. M, something like this. I don't know if I can make like each variable a number, and then maybe t is like number of clauses, and somehow the numbers only add up to t if you're satisfying all the clauses or something. Something weird. How? Okay. Oh, well, anyway, this is enough discussion. So the key idea, actually, is it down here? It is down here. Okay. Our key idea is going to be this. So as far as this kind of conceptual point of how do I map satisfying many clauses at once to adding up to one number, this many to one mapping, we're going to use this trick. The numbers are bit strings, right? 0, 1, 0, 1, 1, 1, 0, something like this. So when I say that two numbers are equal, what would a computer do? It actually compares all the bits. Two numbers are equal only if every bit is the same, right? So at least that overcomes this hurdle of how does satisfying all constraints correspond to two numbers being equal? Because maybe we can like kind of assign one bit to each constraint kind of thing. Does that at a high level? Okay. And I can basically try to pack in a lot of complexity in those bits. That's the high level idea. Okay. So we're going to kind of use many digits. It's going to be massive numbers, which we kind of know has to be the case because if the numbers were small, our algorithm would be fine. So we're going to use massive numbers and sort of use each digit to encode one constraint. Okay, and say, oh, the digits only match up if sort of you satisfy all the constraints. So let me explain. So, okay. So first, as sort of a preliminary step, I'm going to reimagine 3-sat as a sort of subset problem. Okay? So I'm going to think of like having some set of literals. Like x1 is true or x1 is false. x2 is true or x2 are false. And I can take some of them. I can take either x1 is true or x1 is false. And then I think of like, oh, a clause would be like a set of 3 literals. Okay? And say, okay, for this set, I have to take one of these elements in the set. Okay? It's not really a big jump here. But, you know, I want to find a subset of literals so that for every clause, I'm taking at least one of the literals. That's like satisfying it. So x1 or x02 or x3, I have to take at least one of these 3 to satisfy it. And for every variable xj, I can only take exactly one of the 2 literals. I can only set it to be true or set it to be false. That's not really that different than the original formulation, but it sort of massages the language to start looking a little bit more like subset sum. At least the word set is in there. Okay, so this part's not too dramatic. Okay, that looks like the same slide. Okay, now here comes the fun part. We're going to start making big numbers. Okay, and we're going to end up using m plus n digits, in part because they're sort of like m plus n constraints. I have m clauses I need to satisfy, and then for each variable, I can only take one of the 2 literals. There's n here. Okay, so each digit is going to do one of these. And 4 just happens to be big enough based on the construction. So here we go. So for a literal xj, I'm going to create a number, which I'm imagining as a many-digit number. Okay, so I'll call it aj, and we'll have a different one for not xj that will be called not aj in a moment. Okay, and so what's the high-level idea? So we're going to first have m slots, 1 for every clause. Okay, and 1 slot for every variable. Okay, so this is some literal, like xj is equal to true. And I'm going to create some massive number, base 4. And so the idea is somehow like the first slot should correspond to the first clause in a formula, second slot, second clause, and stuff like this. And in here, n slots for each variable, you know, this thing should only appear a 1 for its own. So, okay. So for each clause ci, like take c1, so that would be the first clause slot. Okay. I'm going to set this digit to be 1 if xj is in the clause. Okay. And 0 otherwise. So this is like, oh, it's not in the clause, it's in the clause, not in the clause, in the clause. Okay. So that's going to help us with this first point. And now the second point, to try to make sure that I only take one of the 2 literals. Whatever's the jth one, so this should correspond to like the jth slot for the variables. I'll put a 1 there. Everything else will be 0. Okay. For the opposite kind of literal, you're going to do something very similar. So this is roughly the same slide. You still have the 1s and 0s in the same place. Now, of course, you're looking for the clauses where not xj appears instead of xj. And yeah, okay, so very similar. Okay, so you make you now have 2n really big numbers. Okay. Okay, so here's sort of like a correspondence, right? So on the left, I sort of have like the terminology from our original problem in the set formulation. So I have a bunch of literals, and okay, so what do these kind of map to in our construction so far? So each literal, okay, maps to some long number like just described, and I guess still described on the right, if you can see it. Okay, and a set. So a set of literals is going to correspond to what in subset sum terminology? going to correspond to their sum. So I'm going to think of like, oh, I took these 5 literals, and that's going to correspond to some sum of the corresponding numbers we made, right? So this is like putting, it's adding 1 in all the digits for clauses we're satisfying, and it's adding 1 in all the digits for variables where you take one of the literals, things like this. So if I have this set and I've mapped it to this sum based on our artificial numbers, how do I check to see if our set, in terms of sums, how do I check to see if our set satisfies a particular constraint Ci? So I give you this sum, and I give you a clause, and I say, oh, does the underlying set of variables for this sum, would it have satisfied this clause? Some of the numbers what? Yeah. Oh, so D is our, should be, okay, so in other words, so I have D, right? So I took the set, I just summed up all the artificial numbers we made. So this is just kind of to make sure we're on the same page. Based on this sum, I should be able to tell if the variables I chose, the literals I chose, satisfy this clause. So this is just sort of making sure we understand. We're on the same page. So how can you check? Yeah. And how can I check? So I want to know that I took at least one of the literals, right? And our number should give us this information. But how do we encode this information in our construction? Take like C1. There's like 5 like half hands. We just need one full hand. Yeah. So it's right down here. Maybe I'll zoom in. Okay. So if the numbers were made like this, and I want, let's just say C1 for concreteness, where should I look in the sum to figure out if C1 was taken? Yeah. Here, right? So this will be a 1 for the literals that satisfy the first clause. So in my sum, if that first digit is at least 1, it could be 1 or 2 or 3. But if it's at least 1, I've taken at least one of the literals I want. Okay. So you can see how we're starting to encode all of the logic of a complicated formula in the digits. Okay. So okay. So that's that. So maybe this one will make more sense now. Um, I realize this is like a very unconventional style of thinking. Okay, now our other constraint for our set problem was that for every variable I can only take one of 2 literals, right? Or I should take actually exactly 1. Again, how am I encoding that information in our sum? If I had the sum, how could I check this? Yeah. Oh. Yeah, so these ones in the bottom right, our last n digits, they were putting, you know, I put a 1 there if it was the xj one, right? So choosing exactly 1 should end up with 1, 1, 1, 1, 1, 1, 1. If you have a 2 somewhere, that means you took both literals of a variable. That's not allowed. If you have a 0, you didn't take either. That's not allowed. Okay. So 1, 1, 1, 1. So you can see, yeah, again, how we're Yeah. See, so somehow we can pack a lot of complexity into these numbers, right? Okay. Now, um, okay, so we're getting a little bit closer, right? Yeah. Yeah. Exactly. So we're getting closer at least, right? Because we sort of have these numbers, they seem to be encoding a lot of the logic that we want to satisfy. Now, okay, this is a reasonable way to map numbers, but what would be like a good target T then, right? I would want to give a target and say, can you, so what would be, okay, so I think like the last n digits, this should all be ones, right? For my target T. But what about for these clauses? So we have a problem still, right? Which is that a clause is satisfied if and only if like that digit is at least one. But subset sum doesn't do this at least kind of thing, right? So right now, 1, 2, or 3 in this first slot are okay, and 0 is bad. 1, 2, and 3 are okay, 0 is bad, right? So we need to fix that, right? The only problem right now is that we can't distinguish with the subset sum terminology, allowing 1, 2, or 3 in each of these clause digits. Okay, so that's the only issue left, right? If you can somehow get this greater than equal to an equal something, right? Then we would be done. That's right now the only difference between us and subset sum. Okay, so we're only one hack away. Any ideas? Yeah. Well, yeah, so the question is, so can you just set all the numbers bigger than 1 to 1? Um, well, okay, so maybe we should remember that our goal is to create some numbers and some target to give it to a black box. And I think this suggestion is like, oh, can't we do something in here, right? But that's sort of like not the rules because we want to show that this black box is very powerful. So we have to give it, the input it expects. So we just have to figure out how to deal with this. That's the only flaw left in our reduction. And I'll add, you can create more numbers. There's a huge degree of freedom, right? All we have to do is end up producing a subset sum problem. We're really close. Yeah. So you want to start duplicating these? Well, okay. Well, one thing is that if you duplicate, say A1, you won't be able to use two of them anyway because you can only take one. But you can duplicate. We have lots of room to add numbers, so that's a fine direction. Yeah. Again, we need to come up with a target. So what you're saying is like, oh, this is so dumb. Why doesn't this box just be smarter? We're not allowed to change what's inside the box. We can only change what we give to the box. Ah, okay. So if you said it had to be equal to one, if you said you had to be equal to zero, then that would be saying that you have to not satisfy every SAT formula. You want to just do not equal to 0? So that's the same as greater than equal to 1? Right, but subset sum is going to try to make them equal. Yeah. Okay. Right, right. But you should be careful because okay, so or maybe can I just make this bit 0 or something? Or you're going to make a new digit for the copies? Well, then I would be a little bit careful because maybe you do one A1 and then you do for the copy you do A1 bar or something. But you're not allowed to take A1 and A1 bar. So at some level you just want to make 1, 2, and 3 equal. I mean, they should somehow be same, right? So for example, like, is there some, yeah. Yeah, so can I take a clause like x1, x2, x3 and instead look at not x1, not x2, not x3? So if you had none of not x1, not x2, or not x3, that was equal to 0, then that means you would have x1, x2, and x3. So you're saying that you're like super satisfying all the clauses. But that's a clever idea. So, okay. Okay, so what if I mean, can we try to think of a way where, suppose this poor sum has some ones or something. If it was all threes, we'd be okay or something. We just say it's equal to 3, right? But maybe it's not equal to 3 because some clause you can only satisfy 1 or 2 or something. Is there some kind of hack where if this number had like at least 1, you could easily turn it into 3, but if you had 0, you couldn't turn it into 3 for a particular clause? You can only add new numbers to the system. You can't tell the you can't change the algorithm in the box. We're just feeding input to the box. So we're trying to change, you can change the input. So at some level, okay, I'll be more suggestive. We're going to add more numbers, okay, to help patch over this bug. And what you want to do is you get to create the numbers. So, think about this scheme and what the digits mean. And you want to come think of some kind of number that maybe will let you turn ones, or, a collection of numbers that will let you turn your ones into threes and your twos into threes, but wouldn't let you turn a 0 into a 3. You can do whatever you want. Just make up new numbers. You have some sum and you have a 1 here. You're like, oh, it would be really convenient if I could add something and make it into 3 or something, right? Really close. Uh-huh. So what if we added some like free points, right? Some numbers that are floating around that just let you add 1 to one of those clauses or something, or maybe add 2. So you would be able to take a 1 into a 3, but you shouldn't be able to take a 0 into a 3, which means we can't actually do 1 and 2 because that can take you 0 into 3, but you're really close. You're allowed to duplicate numbers. You can have repeats. Ah, 2 ones. Okay, so we're going to make these numbers. So for a clause I, we'll just make a convenient number that has a 1 in that particular digit for clause I and a 0 everywhere else. And we'll make 2 copies of them. So if you have a 1 in that slot, you can just add 2 more. If you have a 2 in that slot, you can add 1 more. If you have a 3, you can just ignore it. But if you have a 0, you wouldn't be able to get up to 3. Okay? So that's all we'll do. And then that's our hack. And yeah, so now we put everything together. And so now we have the literals, the numbers correspond to literals plus this extra free points, these boosts, and now our target will be 3333 1 and right. And if you have some subset of these things, right, then as you guys know by now, you can only get to 3 for the ith clause if you're taking at least one of the literals to satisfy it. And whoops. D equals 1 means you're only taking one of the two literals. Okay. So that's the whole thing. Yeah, so okay, it's a bit hacky, it might seem a little bit crazy, but it's sort of like a profound statement, right? Like it's saying that, oh, you can actually pack a lot of complexity into numbers. Something as simple as trying to add numbers together can be as complicated as solving like a generic Boolean formula, because actually each bit will give you one more requirement. Okay, so it's like a completely different perspective on numbers. It completely explains why we were able to get an NT algorithm, but not better. Right? Because here actually T is huge. Because it's going to be like, 4 to the n plus n or something, because that's how many digits we have. Okay, so that is it for this. We have a little time, so maybe I'll introduce what we'll do next time. But any questions about this? Yeah. Any bigger number would be fine, but if I chose less than 4, if it was like 3, it's only 1 plus 2 plus 3 is equal to 0, and then the 1 carries over to the next digit, and that seems very painful. So I just chose 4. Obviously, base 4 can be turned into 2 bits. That's very easy. So it's just big enough so you never have to carry any ones. Yeah. Okay. Cool. All right. Any other? Yeah. Well, we know that, well, A, you could change the base. You could imagine doing the same thing. That said, we already showed that you can take any CNF that includes 4, 5, 6, 7, 8, anything you want, and turn it into 3SAT. This we showed a couple times ago. So this is as strong as everything else.